Take a moment to look around you or out the window at the landscape. Whether you are located on a flat plain, a gentle hill, or the peak of a mountain, your surroundings have topography, a unique shape that might include mountains, valleys, rivers, and plains. The shape of the earth is very important for understanding how resources flow across the landscape. But how do we map this shape? With GIS, we need to take the complexity of the Earth's surface and turn it into something that a computer can understand, analyze, and visualize. The answer is a digital elevation model, or DEM. In the simplest terms, a DEM is a grid or a raster of numbers that represent the elevation of the land. Imagine a checkerboard laid over the landscape. Every square on that checkerboard is a single square cell or pixel. Each cell in a DEM holds a single number which represents the elevation of the ground at that specific location. The entire collection of these cells, each with its own elevation value, creates the 3D model of the terrain. DEMs are a foundational concept and data type in GIS and remote sensing. While the term DEM is often used broadly, there are two common subtypes. First, a digital terrain model, or DTM, is a bare earth model. It represents the terrain without human-made structures like buildings and without vegetation like trees and shrubs. It can be thought of as the true shape of the ground if you were to strip away everything sitting on the surface. The second type is a digital surface model, or DSM, which includes everything on the surface of the earth, including the trees, buildings, overpasses, and the ground itself. When modeling how water flows across a landscape, a digital terrain model is usually ideal. However, if you want to understand how water might flow around objects like buildings, a digital surface model may also be useful. DSMs are also useful for urban planning questions, such as where there might be sufficient shade from trees. Historically, DEMs were created using stereo photogrammetry, a technique that uses overlapping pairs of aerial or satellite images to construct a three-dimensional view of the landscape. Take a moment and hold a finger up about 12 inches in front of your face. First, close just your left eye, and then switch and close your right eye while you open your left eye. As you alternate between your left and right eye being closed, notice how your finger appears to move. Your hand is not actually moving, but the angle from which your finger is being viewed is slightly different between your left and right eyes. When you view things with both of your eyes open, your brain is able to merge the two images together, creating a three-dimensional view of your finger. This same principle can be applied to overlapping images captured from an airplane, a drone, or a satellite. Software is used instead of your brain to calculate the angles and heights of the objects from which the three-dimensional views can be constructed. More recently, lidar technology is being used to create digital elevation models. LiDAR, which is an acronym for Light Detection and Ranging, uses billions of laser pulses, typically fired from an aircraft, satellite, or drone, to the ground. The time it takes for the laser pulse to bounce back to the sensor can be measured by a very precise clock. Since the speed of light is a constant, 3 × 10⁸ meters per second, and the laser is firing light waves, it is possible to convert the time delay for the beam to return into a distance, and this distance can then be used to precisely calculate the elevation of the object on the ground. LiDAR can produce very high-resolution digital surface models, which can then be processed to remove the surface objects and create digital terrain models. The third way in which digital elevation models are commonly generated is through radar interferometry, also known as INSAR. With INSAR, satellites use radar signals and combine 2 or more radar images of the same area taken at different times or from different positions. The difference in the signal's phase creates an interferogram, which is then used to map out the topography. The Shuttle Radar Topography Mission, or SRTM, used this method to map the terrain over almost 80% of the Earth's landmass, and the SRTM DEMs are still widely used today. DEMs are more than just a snapshot of the landscape. They are powerful analytical tools used in almost every industry that deals with land. In hydrology and water management, DEMs are essential for determining how water will flow across the landscape and delineate watersheds, which are the area of land that drains to a single point. By analyzing the slope and direction of water flow across the grid, engineers can predict where water will pool and or accumulate and which areas are most susceptible to flooding. In geology and environmental science, DEMs are used to study landslides, calculate the volume of earth moved by a glacier, or monitor coastal erosion. In telecommunications and planning, DEMs are used to determine lines of sight. For example, siting a new cell phone tower requires a DEM to determine which areas will have a clear view of the tower. You certainly would not want to build a tower in a location where the signal was blocked by mountains. In civil engineering and construction, DEMs are used to help guide the placement of roads, pipelines, and bridges, ensuring they follow a proper grade and minimize environmental impact. They are also used to determine areas where buildings should and should not be placed based on the steepness of the land. In defense and navigation, DEMs are critical for creating terrain-aware maps and building flight simulation systems. The list goes on and on. In summary, digital elevation models are the foundation for our digital understanding of the physical world. They are raster or grid representations of the continuous surface of the Earth, where each cell holds a number for the elevation at that location. They allow us to move beyond a simple flat map and step into the incredible analytical world of 3D geography.